Hello everyone, and welcome back to another video where we are going to be evaluating this nice stack exchange integral with a variety of techniques, more diverse than we usually use on the channel. So yeah, let's get started. The first thing I'm going to do actually is integrate by parts. And we're going to be integrating the denominator right here, so that x squared, and differentiating the numerator, the arctan right there. So, doing that, we find that we have minus 1 over x times, I should really write that as arctan, times arctan of x, that's all squared, and then evaluated from negative infinity to infinity. And I'm just going to go ahead and evaluate this straight off the bat. You'll notice that this does go to 0 in two ways, actually. This 1 over x term right here, just in the limit, that should be pretty clear. But then also the inverse tangent squared itself. Because it is squared, it's going to be the same number subtracted from itself because it is an odd function without the squared. So this whole thing goes to 0. And then we're going to have our minus, of course, per the formula. But then we also have a minus there, so I'm just going to make that a plus. Integral from negative infinity to infinity of 2 times tan inverse. I'm going to be writing it as with a negative 1 now that there's no squared involved. Tan inverse of x over x, but then times, by chain rule, the derivative of inverse tangent, so that would just be x squared plus 1 dx. And this function right here is actually quite interesting in its own right, namely because the limit actually does exist at 0, so that makes it a little bit tricky to do complex analysis with. It makes it tricky to do complex analysis with. So to kind of get around that, what we're going to be doing first is applying Feynman's technique. So what I'm going to just kind of do is erase this, slide a t on in here, and we're going to be differentiating with respect to that t. And that right there is going to, let me scroll on down. And that right there is going to, well, actually I'll write this out. So d over dt of, I'll call this f right here, f of t. df dt is equal to then the integral, or well, 2 times the integral, from negative infinity to infinity. But then the derivative of inverse tangent is just, 1 over x squared, but we have that t there. So that means two things. First off, in our denominator, we're going to have a t squared x squared, right, plus 1. But also in the numerator, by the chain rule, we're going to have an extra x. And then throwing in all of our other terms, we have this x squared plus 1 and an x. And do note that these do cancel out. So what we're left with is this integral right here, which doesn't look the best, but it's actually not too terrible because here is where we can apply the complex analysis. Namely, if we just draw our usual semicircular contour, oh, it's a good semicircle this time. We're going to have two poles, one at I, and then another one at I over t. Which one is which, I guess. I don't think it should matter, as long as they aren't the same. That'd be interesting. Anyway, that's for another time. But anyway, applying complex analysis to this, we know that, I'll make this slightly more formal than usual, our line integral over the entire thing is going to be equal to the integral over gamma 1, which is just the integral we want right here, so I'll just call that I, and then plus the integral over gamma 2. But it's as per usual with these sort of things, it's just going to go to 0 because, well, this is expanding towards infinity, and it's just 0. Jordan's lemma, we love it. And by the residue theorem, this is going to be equal to 2 pi I times the sum of the residues. But we know exactly where our residues are, actually, in this case. They're just where our poles are. So, residue at I, and then plus the residue at I over t. So let's actually go ahead and start calculating some of these residues. So let me zoom out a bit actually. And, oh, we can just kind of, well, I should do it off to the side, just to keep all like the answer bits over there. So, the residue at I over t. I'll start with that one. Well, that right there is going to be equal to x minus I over t, and then divided by, or sorry, there really is a limit here, I do apologize. It's the limit as x approaches I over t of x minus I over t over x squared plus 1, and then x squared, it's x squared t squared, but just to make things a little bit simpler, I'm actually just going to factor out a 1 over t squared in the denominator, just to make things a little bit simpler with canceling with that in the numerator up there. So we're actually going to have an x squared plus, yes, 1 over t squared. Yes, that is right. Okay, just wanted to make sure. And then we're going to have our t squared out front, and you can see that just distributes. But it just does make things easier with canceling, because we can now factor, close the parentheses, we can now factor actually the denominator right here. So this is just equal to x plus I over t times x minus I over t. So to evaluate this limit, we can just say, well, these cancel, leaving us with the limit as x approaches I over t of 1 over x squared plus 1 times x plus I over t. Which really isn't bad to evaluate, because we've eliminated the pole, and that's kind of the whole point of the residue theorem. So now once we plug this in, we end up getting, or sorry, there is a 1 over t squared. I do apologize. But just plugging this in, we find that we have 1 over, there should be a squared, 1 over negative 1 over t squared plus 1, and then times 2I over t. And then we have our t squared on the outside, so we can simplify this even further actually to just being 1 over, yes, sorry. We can simplify this even further, saying this is t over negative 1 plus t squared. And then our 2I in the denominator. So that's a residue at I over t, and in my opinion, that's kind of the trickier one. But now we can just calculate the residue at, this is in a different color, shouldn't I? Or I'll do all the residues in one color, then we can switch later. The residue at I. This one is a little bit more straightforward, in all honesty. Boop. Same thing as before, so the limit as x approaches I of x minus I over x squared plus 1, kind of as before, because we've written as x plus 1, x plus I, x minus I, so x minus I, x plus I, and then times x squared t squared plus 1. And you can see here, I mean, rather clearly, that these terms do just cancel, leaving us in the limit with 1 over 2I times 1 minus t squared. So let's go ahead and actually just add up our residues real fast. So kind of moving over here. Can I get both of our residues on the screen as I do this? Yeah, we can try. Okay. So to get a common denominator, I'm actually going to multiply the top and bottom of this term right here, of this residue right here, by negative 1. So now that is a negative. And again, that's just so we have a common denominator, meaning that the sum of our residues is actually just, well, that 1 minus t over, well, our common denominator, the 2i, 1 minus t squared. And you'll notice a couple things about this. First and foremost, that we can simplify this term right here, making it, by factoring again, making it just 1 over 2i times t plus 1. So now that we've calculated our residues, what we can find, I didn't include the 2 in there. Okay. Just wanted to make that, I don't want to lose any factors of 2. Okay. But now that we've done this, we can now just multiply by 2 pi I, leaving us with, draw an arrow, pi over t plus 1. And this right here is equal to our integral. But let's kind of think back to what our integral actually was. The integral we were evaluating was just, I'll highlight it, or not highlight, I'll box it in green. It was just that right there. So in order to actually find the value of the integral from the beginning of this video, we need to do two things. First and foremost, we need to integrate with respect to t. And that's because we applied Feynman's technique, we need to revert that. And then the second thing we need to do is actually just multiply by 2. I'm just going to stick that factor on in the end because you can throw that in and out of integrals and derivatives as you wish. So as I said before, the first thing we're going to be doing is finishing up, I guess, Feynman's technique. So we have this pi over t plus 1 now, and what we're going to do is integrate it from 0 to 1 with respect to t. And the reason we're doing this is because, well, the 1 comes from the fact that, we kind of refer to up here, in the original integral, this right here, that t was just a 1. So that's where the 1 comes from. And the 0 comes from the fact that if we plug in a 0 for that t, we know for a fact that our integral is 0, as inverse tangent of 0 is just 0. So this is probably the easiest integral on the channel that we have ever had, which is nice for change. This is just pi times the natural log of 2 minus the natural log of 1, but the natural log of 1 is just 0. So this is just pi times the natural log of 2. So multiplying everything by 2, because we have that extra factor from before, we find that our total integral is equal to 2 pi times the natural log of 2, which is about like 4 point something. So anyway, that right there is our integral. So I hope you all enjoyed this video, and I will see y'all in the next one.